Ever wondered how a self-driving car navigates a foggy road, or how a robot picks up a cup in a messy kitchen? The answer lies in a hidden world of math and machine learning, where AI learns to make smart choices even when the picture isn't clear. Let's unpack how researchers are teaching machines to think in the dark. Imagine you're trying to track a flickering light in a stormy night. You don't see the light directly, but you get flashes of its position. How do you guess where it's going? This is the core challenge of partially observable systems, situations where the world hides critical details. For AI, this is like playing a game with a foggy window. It has to guess the rules based on partial clues. To solve this, scientists use sequential Monte Carlo (SMC) methods, a fancy way of saying guessing with math. Think of it as a team of thousands of simulated experts, each betting on what's happening. These experts update their guesses as new data comes in, slowly narrowing down the most likely scenario. But here's the problem. Traditional methods were slow, like trying to solve a puzzle by checking every piece one by one. Enter a clever trick from 2013, backwards sampling. Instead of considering hundreds of possibilities, AI now only looks at two potential ancestors for each decision. It's like solving a mystery by focusing on the two most likely suspects instead of every person in town. This cut the computation time in half, making AI faster and more practical. But how do these systems think? Let's break down the brainpower. Many AI models use gated recurrent units, GRU, a type of neural network that acts like a memory. Imagine a student taking notes. The GRU records important clues from the past, condensing them into a memory vector. This vector is then fed into an MLP, a decision-making chef, that calculates the best move and how confident it should be. It's like a chef tasting a dish and deciding whether to add more salt or spice. For more complex tasks, AI uses belief states, a mental list of all possible scenarios. Think of it as a robot juggling multiple what-ifs in its head. To handle this, some models use set transformers, which treat these scenarios like a deck of cards. The order doesn't matter, only the collection. It's the difference between sorting puzzle pieces by color versus by position. The magic happens in the training phase. Researchers use Soft Actor-Critic (SAC) algorithms, which balance exploration, trying new moves, and exploitation, using what works. It's like teaching a kid to ride a bike. They wobble, explore, but gradually learn to stay upright, exploit. To prevent AI from making sudden jarring moves, they add a slew rate penalty, like a gentle hand guiding a wobbly bike. Now, let's dive deeper into the math that makes this possible. Traditional AI methods often treat uncertainty as a hurdle. But here's the breakthrough. Researchers turn the problem into a probabilistic inference task. Imagine your AI isn't just choosing a path, but weighing all possible futures. It asks, what if I turn left? What if I go straight? How might new information change my choices? This is powered by the Feynman-Kac model, a mathematical roadmap for how probabilities evolve over time. It's like giving the AI a compass that points not just to the destination, but to the most informative routes. To make this work, they used a nested sequential Monte Carlo (SMC) algorithm. Think of SMC as running thousands of what-if scenarios, like a chess player visualizing millions of moves in their mind. The nested part. It's like training a detective. First, they imagine possible clues. Then, they use those clues to refine their investigation. This dual-layer approach lets the AI not only track its current situation, but also plan for the unknown. The key innovation. A policy gradient method tied directly to the Feynman-Kac model. This means the AI updates its strategy based on how well it accounts for uncertainty, like a chef adjusting a recipe as they cook, not just following a fixed plan. Traditional methods ignore the belief about the environment, treating it as static. This new approach keeps that belief alive, updating it with every new observation. And the results? In tests, this method outperformed older techniques in tasks like navigating a light-dark maze or solving a triangulation puzzle. It's especially good at balancing short-term goals with long-term planning, like a hiker who first finds a trailhead before rushing down the mountain. So why does this matter? It's not just about better AI, it's about rethinking how machines learn. By treating uncertainty as a signal to exploit, not a problem to ignore, this research opens doors for robots, self-driving cars, and even medical diagnostics to thrive in messy, real-world environments. All this math runs on supercomputers, like the NVIDIA A100 GPU, which crunches numbers faster than a calculator on steroids. The result? AI that's smarter, quicker, and ready to tackle real-world chaos, from autonomous cars dodging obstacles to robots sorting recycling. So next time you see an AI doing something impressive, remember, it's not magic. It's a blend of clever math, efficient algorithms, and a dash of creativity. The future isn't just about faster computers, it's about teaching machines to think in the dark. What will they discover next?